All right. Good afternoon, everyone. We are going to start in 2-3 minutes. Waiting for more to join. Uh, Meanwhile, let me share my screen, and we will start. Okay. So, just a quick recap what we had discussed last time. So we started with why NN is not suitable for sequence modeling task, and then we discussed different types of sequence data in the applications, and correspondingly for different tasks we have different RN architectures for it, and why RN architectures or RN models is suitable for the particular task. And we started with one example, motivating example to understand the architecture of a recurrent neural network with word level semantic. Sorry. Okay. So, and then we started, right. Then we started with one application to see the notations and the RNN working and how the context information is captured in the RNN unit that we had discussed last time. And we discussed formal definitions of context vector and how you calculate it, and the output, and some simplified notations for this, and how the backpropagation works in the RNN, and then what are the problems that are there in RNN which uh, actually solved using other architectures, with the improved architectures. And depending on different tasks, you have different types of RNN architectures that we had discussed. So one to many, many to one, many to many, and many to many when you have input and output are equal. So this we had discussed up in the last class, and we discussed about the gated recurrent unit as well, and full gated recurrent unit and the LSTM that. we had discussed last time. So this was the discussion that we had in the last class. Today majorly we'll talk about transformer based language models, and what are those problems that RNN is having, which led us to the development of transformer based architectures. And so what is transformer, and how transformer maintains long range dependency, as well as the computation that was the major disadvantage with the RNN, where the computation happens one input at a time, or one token at a time, because it's due to its inherent recurrent architecture, sequence architecture, which takes sequence one by one word at a time. uh, then what problems it brings, so we are going to discuss, though we discussed it earlier in the previous session as well. Just to quickly recap, if we talk about language model, and so language models basically are trained based on the three mathematical models: next word prediction, mask word prediction, and replace word prediction. Where when we say next word prediction, so given a text, and it tries to predict the given some words or previous tokens, model tries to predict the next word. So this we had seen in the previous session as well, that how we define mathematical model for sentence. So probability of the whole sentence is nothing but the product of the probabilities of the particular token given the previous tokens. So that this animation shows the probability of I saw a cat on a can be represented by a probability of I multiplied with the probability of saw and given I, and so on. And how you compute that conditional probability, that could be based on some statistical models and gram-based models or neural network-based models, where last time we have seen the RN and how it works. And this is the high-level pipeline that last time we discussed, that given the previous words as an input, uh, that networks gives you a context vector towards the end, and that context vector given to the classification layer, it, that is having softmax that generates the softmax probability, uh, and the word which has the highest probability is taken as an output of that model. And obviously the predicted output and the actual output uh, defines our so difference between those two defines our loss functions, and based on the derivative of loss function we update the weights of the network, and then that is how it is trained. So this was we had discussed last time. And for if so last time we discussed RNN as classification, or some other task. It can be RNN, its variants can also be used for the sequence generation as well. So for example, for predicting the chance of the next word, we feed the sentence to RNN and then get the final YT hot vector and short it based on the maximum probability, and we take the word which has the highest probability. So basically, for taking the probability of a sentence, we compute probability of first output multiplied with the probability of second output with respect to the first, given the first output, and so on. So in RNN, basically, if you want to use it as a language model, we as a first input we pass a zero vector. So this is your zero vector, and this is also a zero vector. Could be a zero vector, or it could be a special tokens that are towards the end and start of the sentence. So that randomly input given to the RNN unit, and RNN unit generates the first word or first token, numerical representation of first token. And for the language model, based on the first, given the y1 uh, as an input and the context from the previous RN unit, it generates the next word, right? So This is inline when you get a random beginning of the sentence at each time, and it generates a novel's sentence towards that. So you can use RNN or its variant like LSTM or GRU or bidirectional LSTM or bidirectional GRU for the language generation as well. And that how vanishing gradient is solved is we had discussed last time. So this was the recap of what we had discussed in the previous session. Now, to understand how transformer works and what is the architecture of transformer and how it uh, is used for sequence modeling, and how you can come how the pre-trained language models have been trained, we'll take one of the application in NLP called neural machine translation task, and which in this task we basically given input or text from one language, the model converts into another language, and that uses a neural network architecture. And we have seen this can be done using RNN as well, with a specific architecture called encoder decoder. Right. So encoder takes the input of one language, and towards the end it generates a context vector final hidden representation. So each RNN unit passes its context information to next RNN unit, and once the sentence is complete, towards the end you get a context vector which have the information or context from the whole sentence of one language given to the decoder, and decoder one by one generates the output. For example, y1, and that y1 is given to the second, which generates the y2, and so on. This sentence is generated given this sentence in one other language. So RNN can be used, and specifically encoder decoder we are using architecture is used for the machine translation task, because length of the input in one sentence or one language might be different from the other language. So how basically sequence to sequence model do this task? So if you see here in this diagram, given uh, text in one language, sequence to sequence model generates one output at a time, and generates the whole sentence one at a time. And the sequence to sequence model, if we unroll it, a detailed version is having two things: encoder and decoder. Encoder takes that sentence, the whole sentence one word at a time. So one by one it takes, and once it reads whole the sentence, it generates the context vector towards the end, which gives to the decoder, and decoder generates one output at a time. So there are two important things. One is the context vector, which so gets the information from the input sentence, or the sentence in one language, and decoder uses using that context vector generates the output in the other language, and it is done one by one. And similar to the word vectors, context is also simply a vector of numbers. So all all the input sequences, basically the text, the word one, two, three, and so on. These are all converted into numerical representation, okay, known as an embedding, word embedding, and the encoder and decoder modules are basically the RNN, right? So word embedding is nothing but, for example, in input sentence consists of three tokens, T1, T2, T3. For each token of word, you have a word vector. Here in this particular example, you have a size of 4, and based on the embedding model that you are using, it may vary size. For example, if you are using word to vec, then it will generate um, around 300 size of vector for each word. And you can think of this vector, uh, as a position of that particular word in the word space. So particularly for this example here, if you have a word G, then if it is representing by this four numbers, so it basically in the fourth dimensional, this basically gives you one position somewhere and represent in the this word space that represent the word J. So n dimensional space में particular location is basically the is your word embedding of that word. And those word vectors basically capture the semantic meaning, and due to this numerical representation of the word, it is possible to perform all the reasoning and arithmetic task on the words. So just if you take a quick recap of RNN, how it works. So initially it takes a hidden state 0, which is a random vector, and it takes the input vector, which is a word token vector. Okay? And RNN unit, what it does is process it. It generates two things. One is the hidden state that is passed to the other RNN unit, and one is the output vector. Right? So this was we had discussed last time, and this is how RNN works. So at each time one input is given, encoder generate one hidden state passed to the second RNN unit, and towards the end, the last hidden state uh, treated as a context vector, which gives to the decoder side. So that final hidden state becomes your the context vector. So it process encoder process each word sequentially. This is important, and generates one hidden state which gives to the second RNA unit, and towards the end, the last hidden state is basically your context which given to the decoder. Why I have emphasize on this terminology, we'll see in the we'll see later on. And so this is also unrolled version of it. So given that sentence, three RNA unit generates uh, hidden state, and towards the end, the hidden state is basically final hidden state is your context vector. This is your context vector, which is given to our decoder I unit, which gives you I, and so on. Other words are generated. So decoder takes context vector and generates translated words one at a time. Again, this is also decoder also producing one by one in a sequence. So we had seen that RNN and its variant like LSTM, GRU, bidirectional LSTM, or bidirectional GRU. These are all useful for capturing the word dependencies or orders, long range range dependencies in the sentence. And some of the problems that RNN have, vanilla RNN have, is solved by its improved architecture like LSTM and GRU. But this architecture, encoded decoded architecture, or even this RNN based networks have two problems. So there are two problems with RNN. What are those problems? One is the context vector bottleneck, because let's say if there is a long sentence is there which consists of let's say 50 words, So this input sentence, which have 50 words, uh, if it is given to the RN init, the last context vector that you get, uh, it has the information from all the 15 words, or context from all the 15 words. The problem is your context vector is fixed. For example, so context vector is nothing but the some collection of numbers having some fixed memory. For example, if we talk about vector of size 10, so you can put 10 values here. So that fixed size context vector want to capture the information from all the words, especially in the long range sequences, uh, creates a problem. Why creates a problem? For example, let's say uh, this screen that you see here, the screen that you are seeing here, white screen. And right now, I have written two sentences: context vector bottleneck, attention address to the bottleneck, and so on. If you put more sentences here and more information here on the board, so it there will be one point of time that it would be not easy to understand what is written on the board. So if you put lots of information in a fixed memory size, eventually uh, it will be hard to retain all the input information. So that is the same problem that context vector bottleneck have. So for the long range sequences, uh, there might be loss of information. So this is one problem. One is uh, so so this is one problem, and another problem was sequence to sequence. So what happening? So RNN are inherently process one word at a time in a sequence, which makes them computationally slow. And if I say computationally slow, uh, okay, so let me. So they are computationally slow. Why? Because they are taking one word at a time. So basically, they are processing input in a sequence. So why it is a problem? Because if we have a large corpus or large data is there, uh, then training a simple RNN or even its variant like LSTM or GRU, it will take a lot of time and a lot of computation. With some which with the increase of size, with the increase in the data set or data size, it becomes computationally infeasible. So that is the reason you don't have any pre-trained model. You didn't have the pre-trained model in tech side. So in NLP side, before 2017, there were no pre-trained text model. You might have heard various pre-trained model in case of computer vision or images like VGG16, VGG19, LXNet, efficient net, and so on. So you might have various YOLO is there. So you have different pre-trained model in image side for computation task, and you can use those pre-trained model and fine tune on your data set or on your small problem specific data. However, in NLP, there was no pre-trained model, and what was the reason? This was the reason, because it is computationally very hard to train those language models on a vast amount of data. So earlier, there was no pre-trained model was there. Now, uh, So it has two problems. One is this, because it want to capture the ordering of the sentence, uh, it is computationally slow due to its inherent recurrent architecture, right? And second one was the context vector bottleneck. So context vector bottleneck brings the information loss, because it will be hard to retain all the information in a fixed size window of context vector. So researchers have proposed different architectures. In 2000, I think 16, they came up with sequence to sequence model with attention mechanism. So attention mechanism have first introduced, which solves the problem of vector bottleneck. So that solves the context vector bottleneck. So what attention mechanism is? So basically, what you do uh, in earlier, what we are doing in coding stage, you are having the last vector as a context vector. In at sequence to sequence with attention model, this is not, we are not talking about transformer. This is before the transformer. In sequence to sequence with attention model with attention, instead of taking final vector as a context vector, we collect all those intermediate hidden state together. You can see here, for three inputs we are having three hidden states, and the all three hidden states are collected, and these hidden states, all the hidden states are given to the decoder side, uh, to find out the which hidden state is relevant. So why what is the motivation behind it? So let's say you have words W1, W2, W3, W4, W5, W6, and so on. So what is happening after each RNN unit? You get one context vector which has the information from all the words. And suppose one particular output, uh, YT, generation of YT uh, does not depend uh, on all the words. It might be possible that the relevant word for the current word is only W3, or information or hidden state, or basically the context from W3 only. So W4, W5 are irrelevant. So why we are giving all the information into one context vector? Why not just context vector uh, have the information from the relevant words or the relevant tokens only? So that's where attention mechanism comes. Instead of taking the final context vector, it collects uh, all the hidden states, and these are given to the attention decoder RNN, where each decoder unit having the attention mechanism that find out which hidden state is important to generate the word I. For example, in this particular example, the I, and out of these three, which are important to generate M, and so on. So instead of having one composite or combined context vector, now attention mechanism, using attention mechanism, it is find out that which context vector is which hidden state is relevant to current output. So it is based on calculating attention weights to emphasize important encoder hidden state at each decoding step. So how it is done? So decoder uses attention weights to generate each word based on the most relevant input token. So if you see here, suppose, so At decoder side, you have all three hidden state at once instead of one hidden state. Score attention score is calculated from this hidden state for each vector. We'll discuss later on how this attention weights is calculated. Right now, just think about it. Some score is calculated, and based on that score, uh, we squash it that scores and turn it into probabilities using softmax. So once it is turned into probabilities, so for example, 0.96 probability suggests that okay, so this hidden vector one is highly relevant, and these two are not so relevant, right? And then this software score is multiplied with each vector, and when you multiply fraction value with each vector, in turns, if the value if is high, then the vector values will be high. So if you see here, these two are not relevant vectors having minimum values, and we add all those vectors, gives you the composite uh, vector, context vector. So that calculates the context vector for time step. So instead of taking all the so instead of taking the final hidden state or from the encoder, all the hidden state from the encoders are collected, and it is finding out which one is important. So at the last, when you get a single context vector, this is basically nothing but having the maximum information from the hidden state one, because hidden state one is relevant for generating one output. I hope you are getting my point. If you have any, so okay, so one question is there related to quiz. So there will be two quizzes. One is already conducted, and one will be conducted after few sessions, maybe around 14. So there are two quizzes only. So how many of you understood this tension mechanism? So what happens here, after encoding stage, once you get all the hidden states at each RNN unit, attention mechanism calculates the attention context vector, right? Which which concatenated with the hidden state, and given to the softmax layer, gives you the output vector, and that is passed to the next RN unit, and next RN unit then do the same task, takes all the hidden states and find out the relevant one. In case of next RN unit, the second version one is important, and so on. So this is how it generates the output, and this I is given to as an input to the next RN. So the problem of context vector bottleneck was solved in sequence to sequence with attention mechanism, but uh, if you if you still see the generation of output and also the calculation and computation is still sequence to sequence. So though context vector bottleneck is solved, computation is still slow. So then researchers have come up with a alternative approach that uses algebraic operations to uh, compute the long range dependencies and to handle the long range dependencies. And those that alternative approach enables the parallel computing so that a model can be trained on the large corpus, which is not possible on the basic RNN or LSTM based networks. So how many of you understood this? So yes or no? So we discussed sequence to sequence model and then sequence to sequence with attention mechanism. If you understood these two things, then it is easy to understand transformer with the self attention. Okay, should we go ahead? Yes or no? All right. So let's move further. So in sequence to sequence attention network, you give the input embeddings to encoder. From encoder, instead of taking final state, you collect all the hidden states, which is given to attention based decoder. So each decoder unit having attention mechanism to generate the output, and then you get the output. Uh, and there could be various there are various versions of it. So you might you can collect all the hidden state from the input sequence known as a global attention, where each decoding unit collecting all the hidden states and computing the output, right? Or you could work with a local attention mechanism where instead of taking all the hidden state, you take some of the hidden states as a context information to generate one output. So these are the two variation. So that heat map shows that okay, so given this input uh, in the output, which word is relevant to which particular word. For example, J is relevant to I. Uh, so hidden state one is important. Shows that okay, so these two are relevant, and similarly for other words, the relevancy is shown in the vision. So that helps in interpreting the model behavior. So, what the benefits of attention that it improves the translation quality, especially with the long sentences, and it also enables the model interpretability. And there are lots of application of sequence to sequence with attention, machine translation, question answering, speech recognition, conversational AI, and so on. So that these are the concept that we studied, that sequence to sequence architecture and RNN as an encoder and decoder. And then we discuss one problem called context vector bottleneck, which solved using attention mechanism. Right. Then in 2017, one of the researchers proposed uh, transformer architecture, which And the paper name is paper title is Attention is All You Need, proposed transform architecture, which solves the second problem that those networks were having, which is the uh, sequence computation, which makes them hard to train on the large data set. So if we talk about transformer, so what is transformer? So it is a deep learning model that uses self-attention mechanism to process the sequence. Now, when we say self-attention mechanism, so we had seen the attention which calculates the relevancy among the words. Self-attention means given a sentence uh, having words W1, W2, W3, W4, W5, and so on. Given the sentence, in the same sentence, it calculates the relevancy among the words. For example, W1 relevancy with the W2, W3, W5, and so on. It is calculated similarly for W2 relevancy with W1, W3, W4, 5. So self-attention mechanism calculates the relevancy among the words to process the sequence. So the earlier RNN networks struggle with the long range sequences, and they are not suitable for tasks like translation, and they suffer from the context vector bottleneck. For example, here in the sentence, when Sarah, I believe, software engineer, discovered critical bug in the system, she immediately informed the manager. So she is relevant and depends on the uh, Sarah. So, for example, whether here should be she or he, it depends on the word or the name that is there. Yeah. So, in long range dependency, where you have many intermediate terms, context factor becomes the bottleneck that we had seen. So, in attention, a mechanism, we saw that it focuses on the relevant part of the input sequence by using the attention mechanism at each decoder unit, but still it requires sequential processing. So still, everything is done in a sequence which makes it computationally hard to train on the large data set. That's where transformer came into the picture, which solve these issues using self-attention mechanism. And this basically transformers enable the parallel processing of the sequences. So given input, transformer transforms into uh, another gives you the output, and the transformer enables the parallel processing. This is an architectural overview similar to encoder decoder architecture. It consists of two parts. One is the encoder, and another one is decoder. And there is no, I mean, unlike encoder decoder state, they might be having n number of encoding uh, layers. So just to give you idea here, and we'll discuss everything in detail. Our a quick overview: encoder takes the input, and unlike sequence RNN where it takes one word at a time and process it and generates this context which is given to other unit, it takes all the input at once. Now, if we give all the inputs at once to the network instead of giving one by one, what problem will it create? Yesterday we discussed in the initial 5 minutes. If we give all the input at once, what would be the problem? अगर हम सारे इनपुट वर्ड एक साथ देते हैं आर्किटेक्चर को, तो क्या प्रॉब्लम होगी? व्हाट प्रॉब्लम इट विल क्रिएट? एनीवन? Sequence, yes. So sequence will be lost. So the ordering will be lost. Uh, Memory overload is not an issue nowadays. Assuming if you have a large memory, the memory is not an issue. Uh, if you give all the words at a time, at the same time, then the ordering will be lost, and which is the one of the primary requirement of sequence to sequence model, right? So that those words as an input embedding is not directly given to the encoder, it is added with the positional encoding. So those embeddings are added with the positional encoding to make it position aware. And for positional encodings are calculated using the sine cosine functions, and that the resultant value is added into input embedding. Then the output becomes the even though we are giving it once together, the input embeddings are now position aware. So it enables us to give all the inputs at once. And each encode and encoding side, you have many encoding layers. You might have n number of layers of encoding, and in that particular paper, researchers uh, use six encoding layers. So you might have n encoding layers, and each encoding layer have two main functions: uh, attention mechanism and the feed forward. So the input embedding, nothing but the word vectors. Uh, all the input tokens to a vector are mapped using the positional encoding before applying to the self attention, because there is no notion of order awareness in self attention, so we have to add the position coding. We'll talk about it later. And then it is given to multiple encoding layers, encoder layer, and each encoder layer in past output of each encoder layer is passed to the next encoder layer as an input, and towards the end, that it, the output is given to the different decoder layers, where decoder layers calculate the output. And so output of last encoder layer is used by all decoder layers. And this encoder decoder architecture is made up of multiple identical layers. So encoding side, you have multiple encoder layer. On the decoder side, you have multiple decoder layer. Okay. And each encoding layer have two main tasks: self attention mechanism and this feed forward neural network. So each encoding layer takes the input and create a representation as an output. And how it is done, how it create the representation. So it has self attention and feed forward sublayer. Whereas in decoder side, you have feed forward and the self attention, but you have an extra uh, sublayer called encoder decoder attention that generates the output sequence. So to understand how it works, starting from encoder side, Consider an example of thinking machines. So this is our sentence, a smallest sentence having two words only, W1, W2, or you can call it X1 or X2. Uh, so that each word in that sentence can be taken as an input embedding, thinking, and machines, and passed to the self-attention networks that gives you the contextual embedding. And when we pass to this contextual embedding to feed-forward network, you get the representation of it. That representation is basically your representation of that word. So, and each self-attention, what it does, it calculates the relevancy among the words in the sentence. It checks how much x1 is relevant to x1 and x2, and it also calculates how x2 is relevant to x1 and x2 both. So in self-attention, it allows each position in the sequence to attend to the all other in the same sequence. So for example, the sentence the animal didn't cross the street because it was too tired. Uh, it is relevant to the or an animal, highly relevant to the animal, and also somewhat relevant to street as well, and to as well. So that relevancy is basically mm, the notion of contextual embedding. So how now earlier that I emphasized that earlier sequence model works on a in a sequence manner, uh, generating doing the computation in sequence, which creates a problem. So in transformer, it uses alternative mechanism to calculate the relevancy using the self attention, and it the idea was motivated by using the algebraic operations, vector to vector, vector to matrix, and matrix to matrix. Because if you have algebraic operations are involved for the computation part, then it can be parallelized using deep learning libraries, right? So GPUs can exploit this algebraic operations to compute to do the computation in parallel. So in self attention, what it is done, each word vector is converted into three vectors. So three vectors are computed from each word in the sequence: query, key, and value. And the idea came, so analogy, if you want to see of this query, key, and value, you can think of how you search over the internet. For example, if you go to the Google, so if you go to the Google, let's say, okay, so on Google Scholar as well. So for if I write self attention, so that word is my query that I'm giving for the search. When I search it, you see the various options I have, and each options have some link header, you can say. So this you can think of it as a header, and this is your content is there. So title is basically is your header. So you can think of this as a query, and how we search it. So when we search a paper, so we check okay, uh, which key. So you can think of this titles as a key value, and you think okay, so which title is more relevant to your query. So then suppose this title is more relevant to your query. So basically this key is how similar it is to the query, and if it is similar to this key, then you go to this, and you this the content you can think of it as a value, right? So similarly, here as well, each input is converted into three query key and value. So each word embedding is mapped to get three vectors. And how we are going to get those three vectors? Basically, with the help of training. So that can be done using trainable parameters. So that involves the weight matrices. So for query you have a weight matrix. For q you have weight matrix, and for value you have weight matrix. That if the word is multiply with word vector is multiply with this weight matrix, then you get the resultant query vector. Similarly, when you x2 multiplied, then you get the q2. Similarly, when you x1 is multiplied with the key weight matrix, then you get key. And you can think, and the dimension you can easily see. Uh, if you want to get a query vector of size 3, then the weight matrix size is 3 into dimension of word vector. So dimension of query and dimension of input embedding word vector. And these are, since these are the word vectors, so obviously so these are all the matrices, so obviously these matrices will be learned during the training time. Okay, so before moving ahead, just a quick overview. The transformer architecture is used to resolve the one of the problem called sequence processing, and to enable parallel processing, parallel computing. Instead of giving word embedding directly, it first converts the word embeddings into three vectors called, each word is converted into three vectors: query, key, and value. And the computation is done using trainable parameters. So you then there are some weight matrices involved, and these weight matrices are trained during the training time. And once it is trained, you can say this q1 key1 and value 1 represent that x1, and this q2 key2 and v2 represents x2. So we'll take a short break of 5 minutes, and then we will understand how this uh, query key and value vectors helps in calculating the attention mechanism. Meanwhile, if you have any questions, you can write it on the chat. Quick question? Do you have any question? If not, we'll take a break of 5 minutes, and then we will start again to understand how our self-attention works, and how transformer architecture is trained. Okay, welcome back. Uh, so, in self, so what we were discussing about the encoding part of the transformer, how it works, and the key idea called self attention, uh, how it is computed, and I just ended my discussion where uh, I explained each word of the input embedding is converted into three vectors basically: query, key, and value. And these vectors are computed uh, using the trainable parameters, having weight matrices, corresponding weight matrices are involved, weights are involved. So once each word is used to get the query key values corresponding to each word, attention score is calculated. How it is calculated? For example, there are two words x1 and x2. So for x1 you have a corresponding embedding. Using this embedding you get three query key and value, and using this query, similar to the Google search, using this query you compare and you find out the similarity with all the keys available. So key corresponding to this thinking itself, and the key corresponding to other words, and if you have more words then you might have more keys as well. So query is uh, checked for similarity with all the keys. In computation, how it is done: so the query and key, you calculate the dot product to calculate the similarity score, and once that similarity score is there, it is scaled by dividing the square root of the dimension of the key vector, which is one of the scaling that researchers have proposed to scale down for the ease of computation only. And once this scale dot product is calculated, a softmax uh, is applied to squash that output or score to make it to convert it to into probabilities and get the values in between 0 to 1. Once you get the softmax score, this softmax score is multiplied with the value vector to get the final value vector. Right. And not only with the own key, uh, query vector is also multiplied with the check the similarity with other keys of other words. So for example, here there are only two words. So q1 is also multiplied with the key 2 to get the similarity score, and that is scaled by dividing it with the root of dimension of the key, and then softmax is applied to squash the value uh, and brings the probability in between 0 to 1. And this softmax score is multiplied with the value to get a value vector. Since this value is low, then eventually the all values in the vectors uh, will be small. And once you get this all the value vectors, uh, these are all the added together get a single contextual embedding. And obviously these, so this light color of v2 shows that v2 have small values, uh, smaller values compared to the v1. So uh, eventually the z that you get is dominated by the v1 only. So that in turns represent that, okay, so uh, your x1 is relevant to x1. Similar, the same operation is done for the machine's other words as well, which calculate the similarity with itself and other words. then you get another contextual embedding for other word as well. So how scale dot product attention calculate? You use dot product between query and key for all the keys to compute the similarity score. You scale it by dividing it to under root of dimension of key. You apply the softmax to get the attention weight, and you add all the v's weighted by the attention weight. Then eventually you get towards the end the contextual embedding. Um, beauty of using vectors, notion of vectors, that you can perform those operations, algebraic operation, all at once. So instead of taking one vector at a time, you can calculate uh, self attention, all self attention at a time. So you take, instead of taking single word vectors, you take the whole sentence where each word vector is represented by one row. So you get input matrix, embedding matrix, multiply with the query uh, weight matrix, gives you the query matrix. So instead of query vector, you get the query matrix at once only. So where each row represent one query vector for different word. And similarly, you calculate the key matrix and the value matrix. So instead of uh, using having multiple operations using loops, you can perform those operations in a single go. So in matrix representation form, you take the query matrix, multiply with the transpose of the key matrix, that gives you similarity score. You scale it by dividing it with the under root of dimension key, and once you get this, you squash it using softmax uh, activation function, and then whatever the result that you get, you multiply with the attention what you multiply with the value matrix, gives you the z contextual embedding, where each row represents the contextual embedding of for one word, right? So you can perform those operations at once. uh, so single head might so if you have self attention, one self attention, then layer, or known as a head as well, then it might be trying to capture one notion of relevancy among the words. However, in your sentence, your words might be having other notion of similarity or other notion of relevancy as well. So instead of using single attention head or single self attention mechanism, you can use multi head attention net as well. So you can run attention multiple times in parallel, and you might have, instead of having one head, you might have uh, multiple heads that capture the different notion of relevancy. For example, one head might be capturing relevancy of it with the an animal. Other head might be capturing relevancy of it with tired, and some other relevant word like straight and all. So, for example, word it, one head attends to animal and second head attends to tired. So if you have multiple heads, so all heads, for all heads, you calculate the query key and value matrix. So given an input x, attention head 0, which is trying to capture one type of relevancy, with its own query key and value matrices, and another attention head having other uh, notion of query key and value matrices. And you might have multiple heads. In research paper standards, they shown eight heads. So if you have, let's say, eight heads, so each head might be giving you attention at giving you the one contextual embedding matrix. So you will get eight attention heads. So you will get eight contextual embedding matrices. And so in the architecture that we have seen okay, so this was the architecture. So in that architecture, what we had discussed now, it we understood that okay, so your Z, so your input is made positional aware using by adding positional encoding, and that all the embeddings are given at once. So we had just covered the multi-head attention where you get the contextual embedding. Now after multi-head attention, you see there is a add and normalization layer as well. So normally add and normalization layer having two operation, addition and the normalization. So in addition, uh, you add the original input to the contextual embedding just to uh, avoid the avoid the just to avoid that okay, so the original information is not lost. So you add that into contextual embedding, as well as you perform the normalization to just for the computational purpose. So and then after that you have a feed forward network. So once the uh, output of multi-head attention is calculated, it is passed through a feed forward network and it applied to each position. So you concatenate all the attention heads, for example, Z0 to Z7. And when we say we are passing to feed forward network, we are basically performing algebraic operation by again another trainable parameter matrix. Let's call it WO, and you get the uh, info the output, which basically captures the notion of relevancy among the words, okay, or contextual information Z. So what the story so far in encoder side, we take the input, we have the weight matrices corresponding to all the heads trainable parameters. Using those weight matrices, you calculate the query key and value matrices for all the heads. Eventually, you get the contextual embedding corresponding to each head. You concatenate all the attention uh, bits, so contextual embeddings, and you multiply with the weight matrix WO, which produces the output of the layer Z. Right. So this is the computation happens in one encoding layer, encoder layer. Initially, we I just discussed about positional encoding. So because uh, since there is no notion of ordering in transformer, if the text like machine thinking and thinking machines, though both having the same words, however the order is different. That's why they have different meanings. Similarly, lion killed a man and man killed the lion. Both have the same words, but have a different semantical meaning. So we want that the order should be aware in the transformers, so that the mean they are treated as a different inputs, not the same input. Therefore, we add the positional encoding. And normally these position encoding are nothing but the sine and cosine function of different frequencies. So your input is added with those positional encoding, gives you the embedding with the time signals, and it allows the model to learn the positional information. So once you get the Z, you have a add and normalized layer. So you add the original information to the Z and you normalize it to make it computationally easy, and then you pass it to the feed forward network. Again, add and normalize gives you final output. So what we have discussed that on encoding side, you have multi-head attention, feed forward, and add a normalization layer in the encoder side. On the decoder side, you have a multi-head attention, however, a masked multi-head attention, and encoder decoder attention, which is extra in the decoder layer. And you have feed forward and added normalization. Feed forward and added normalization works similar that we had seen in the encoder side, and the two masked multi-head attention and encoder decoder. So why we are using masked instead of simple multi-head attention in the decoding side? Because decoder is going to semantically generate one word at a time. So what we want to do that the attention should be calculated with respect to the previous word that have been generated, not with the future word. So when we calculate attention score, when we multiply q with similarity score, when we multiply q with the q key matrix, then the attention score that we calculate, we mask the for the future tokens. For example, uh, for query one of input one of first, so word first of the input one, we calculate the attention score with itself only, and for q2 we calculate with the key 2 and key 1 as well. So previous context we calculate, we mask the attention score of the future tokens, and eventually get the attention weight after applying the softmax. So it prevents the decoder from attending a future positions during the training time. This is for the training time, because the decoder is going to train for generating a sequential data. So we want to focus on the previous words only. And output of the top encoder is transformed into K into V. So once you
Sir, I
get
think somebody had a question about
yes,
multi-head.
okay. So in a single head that we discuss, okay. So in attention head, self attention is computed, and each input is converted into three vectors, query key value that you might have understood this, and a single head basically trying to capture one type of relevancy among the words. And when we are calling self attention, means in the same sentence among the words. So first it is mapped to query key value, and then using scale dot product and the some other operations, you calculate the attention weight, and you eventually get the contextual embedding. So that contextual embedding consists of information that so x1 is relevant to x1 only, and less relevant to x2, and so on. And if you have multiple words, which words it is highly relevant, the contextual inform uh, you get. So one second. Okay. Sorry. So when we say multi-head, so multi-head means you might have multiple heads. So one attention head might be capturing one notion of relevancy in the same sentence. Another attention head might be trying to capture another notion of relevancy uh, in the same sentence. So when we are saying one multiple head, so each head had its own query key value matrix, and thus their corresponding weight matrices are involved to calculate this. So you can have multiple heads, multiple attention heads means multiple self attention weights that you calculate, and they might be capturing different aspects in the sentence. Let's say if you have 8 heads, so for 8 heads correspondingly, see here. So for, let's say you, this is your input word sentence thinking machines. So corresponding this you have sentence matrix, embedding matrix. So for, let's say if you have 8 heads, so for each head you have query key value matrices, and using this you calculate the contextual embedding. So you will get, corresponding to each attention head, you get uh, different contextual embedding, and then you, towards the end, you concatenate in and you get a single contextual uh, matrix, embedding matrix. So for giving the answer of your question, multiple heads are basically uh, multiple attention weights you are calculating to capture the multiple notion of relevancy among the sentences. So ऐसा नहीं है कि एक टाइप की रिलेवेंसी है वर्ड की. फॉर एग्जांपल किसी वन एस्पेक्ट में वन पर्टिकुलर वर्ड इज रिलेवेंट टू अदर वर्ड, अगर इन अदर एक्सपेक्ट इट इज relevant to other words. For example, यहाँ पे एक there was an example. For example, one word it in the same sentence. So both sentences are same if you see here. Uh, in one aspect, it is relevant to animal. However, in other notion of relevancy, it is relevant to tired. So one head is trying to capture this type of relevancy, and another head trying to capture this type of relevancy. And all the attention heads are calculated in parallel. Okay, so from the encoding layer, you have there is a decoder layer as well. So in decoder layer stack, each decoder layer have masked multi-attention, encoder decoder attention, and the feed forward and add and norm. So add and norm and feed forward work the same like in the previous, so that we had discussed in coding layer. Instead of having multi-head attention mechanism, you have a masked multi-head attention network, because on the decoder side, uh, hi- semantically, it is trivial to see that we want to generate one output at a time, right? So given a sentence, you are converting it to another sentence. The output is generated one word at a time. Even on the large language model, on the LLM, so GPTs that you write, if that generates a sentence, you can see it generates one word at a time. So that output is to be calculated one word at a time. So what we uh, use auto-regressive approach of training. Auto-regressive models are those models that generates one word, that gives output one at a time. So during training time, to make this auto-regressive approach, mass multi-attention network, when we calculate the attention score, we so not we basically in this architecture, the uh, future attention score are masked, so that these are not used to calculate the self attention weight. Because when we are so when the decoder is with respect to the first word, it should only look at the first word, and when working with the second word, computing with the second word, it should only calculate the attention with respect to the first word and the second word only, not with the future. So in an encoder decoder attention network, last output of encoder of the last encoder is transformed again into k into v, k and v, so key and value, and this key and value is passed to the decoder for by the encoder decoder attention layer in that. So here, if you have sentence in one language, you have embedding with the position that it goes to the encoder with all the encoder layer. Towards the end, you calculate two matrices, key and value, and that key and value matrices are given to the decoders layer, all the decoders layer, and each decoder layer, it is given to the attention module, and your decoder is auto-regressive. That's why we masked it. So auto-regressive means we the decoder generates one output at a time. So output I, then M, then A student. So the output with the embedding time signal. So at step one, the future one are masked. So it decoder generates only one out, and so on. However, again, though in auto-regressive approach, it looks like okay, a decoder is working one at a time. So during the training, it uses teacher forcing training. Teacher forcing training means, let's say this output input is given here, and that transformer is generating output 1, and instead of after the output is calculated uh, and giving it as an input to the next, as a next embedding, next input, what we do, the expected output that we know, we forcefully fed at once to a decoder, so that uh, the outputs of the next decoder based on the targeted input only. So training, for the training we use teacher forcing approach during training to make the decoding parallel. Instead of one at a time, we pass the targeted output at once. Since even if you understood some of these parts in the theory, the main key points is every operations is done so every operations or every computation is done using algebraic operations, that is basic linear algebra operations, uh, matrix to matrix, matrix to vector, or vector to vector. So it enables that we can perform this computation in parallel. And if we can perform this in parallel, we can actually train it on the large uh, corpus or large data sets. So when transformer was introduced in 2017, it enables the uh, pre-training uh, of language models with large corpus, and from that's where it started, and it enables the pre-trained transformer in the text side. And so there are various variants. You might have heard about BERT by Google, which only uses the encoder part of the transformer, because the whole objective of BERT is to give you the embedding of the input, not to generate any output, just to give the embedding of the input. So that's why BERT uses only encoder part. In case of GPT or GPT variants, it uses decoder only, where because uh, GPT generates the output or natural language output, and it generates one at a time. So uh, it uses only decoder part and some other like T5, which is used for various applications like machine translation, where input is in one sentence and output is another sentence. Both encoder and decoder are needed for it. Okay, so any questions? If you have any question, please write it on the chat. Then give few details about how to calculate. So for positional encoding, there are various mechanism and various functions are used. Uh, how so the various functions like sine and cosine functions have been used, and so if you add unique vectors, and those vectors are based on some patterns like which is given by the sine and cosine functions, then you can distinguish between the position of the words. So apart from sines and cosines, there are uh, other mechanism as well. So you can uh, you can find out the literature, and you can find out what are other ways for adding the uh, notion of signals there in the embedding. So basically the idea is uh, sine and cosine function have this notion of frequencies, right? So, and even the original paper, the transformer that proposed uses that sine and cosine functions. So it is not something like it is not learn the absolute positioning. It basically learns about the relative positioning of the words. And also uh, even let's say if you do not want to use those sine and cosine function, you can learn the positional encoding during the training time as well. So you can add learnable parameters with it. And whenever we say, okay, so add learnable parameters, basically you add more matrices and more parameters into it. Okay. So that enables basically parallelization. So transformer are using alternative approach to calculate the notion of relevancy among the sentence. So that enables the parallel computation, and it can also handle long range dependency. And obviously that requires large amount of computational cost and the data. However, it enables that on large data it can be trained. So the key concept that we have studied, so transformer is nothing but an encoder decoder architecture having self attention mechanism. The idea of positional encoding is also there, and the multi-head self attention network auto regressive decoding is used, and masking and encoder decoder attention. And if you see the architecture there, one thing is minute, which is not I've explained. If you see here in the decoder side, uh, so if you have a sentence pair input and output. So output sentence, you can see here we give it as a shifted right. So in auto-regressive model, when the model is going to build one word at a time, initially the input for that word should be, for the first output would be nothing. So uh, special tokens are added to the towards the start and the end of the sentence, which those special tokens and the inputs are shifted, and that is special tokens is given as the first input. So the output is actually shifted right. So that is one thing. And whatever the output that we expect, we feed at once. So though decoder uses auto-regressive decoding mechanism, it to enable the parallel training, we use teacher forcing approach where we force you, okay, so this is the output of the uh, what previous layer. And so how we how transformers have enabled and large language models have came into the picture, we'll see in the next session, where we are going to talk about LLMs, talk about RAG-based system and agentic AI-based system. We'll talk about those models in the next session. So that ends to this session here. If you have any more questions, then you can write it on the chat. I'll give the answers of it. Otherwise, we'll have a hands-on session from 4 p.m. Where you are going to see how you can use pre-trained models uh, in the. So you'll see the example of pre-trained language models in the hands-on session. Yes, 4 p.m. you can join back for the next session. And meanwhile, if you have any questions, you can write it on the chat. Uh, Myself or Mayank will give the response for it.